All right. So let's get started. So again, today what we're going to do is just review Chapter 8 material. And actually where I want to start is where we left off last time, or where we concluded the chapter, because that, with all the technical difficulties last class, it didn't get recorded. So let's just get it here so we have it for our records. This is talking again about epoxides, which are these cyclic ethers, specifically these three-membered rings. All right, so we got a triangle with oxygen in it. And these will react with nucleophiles, so I'm just going to do generic nucleophile here. All right, and y'all are going to take a second and tell me what the product of this reaction is. Oh, and we have to have some sort of a solvent like water in there as well. All right, and these triangles are very unstable. Remember, carbon doesn't like to be kinked into a triangle. Its bond angle is way smaller than it wants to be. So these epoxides are very reactive. They undergo these ring opening reactions. Okay, so our nucleophile is going to attack one of these carbons, and that's going to cause this bond to break, so our ring pops open, right? Opens up. And so what we get is a nucleophile attached to one carbon, and then an alcohol group on that carbon next door. All right, if I color my carbons here, the nucleophile attacked this blue carbon, so it's got a new bond with that blue carbon. And then this bond broke, right? But that oxygen is still attached, we'll use green, to this carbon over here, this green carbon. That's how it becomes that OH group. All right, so these are these ring opening reactions of epoxides. So now let's look at some sort of real epoxides and nucleophiles here. All right, so in this first example here, we have a negatively charged nucleophile. Okay, so our nucleophile is going to attack one of those carbons in my ring. So I'm again just going to color these. And when it does, that causes that ring to open. All right, so I'm going to draw my two carbons from my ring. I'm going to keep my coloring here just so we can see what's what. This carbon's green, this carbon's blue. All right, I got to include these methyl groups on there because those were in my original molecule, right? Got to have the same number of carbons. But now I'm going to attach that nucleophile to my green carbon, okay? And it gets attached at that oxygen for my negatively charged nucleophile. The blue carbon then has what group on it? The alcohol group, an OH. It still has this carbon, this oxygen bound to it here, okay? So remember, with our negatively charged nucleophile, that negative charge becomes our new bond. All right, that's why I connected that oxygen to the carbon. And it is quite literally that pair of electrons, right? If we were drawing in our pair of electrons on this oxygen with a negative charge, we'd have 3 lone pairs. If we draw our lone pairs on our neutral oxygen of our product, there's only 2. Right? There's 3 on the one side, 2 on the other side. Where did that extra pair go? This is the pair of electrons that forms that new bond. Okay, so that's why when we have a negatively charged nucleophile, that negative charge, that pair of electrons, becomes our new bond in our molecule. Okay, we can also have neutral nucleophiles. In the case of epoxides, they'll react with neutral nucleophiles under acidic conditions. So that's what this H plus means here, just that we have acidic conditions. Okay. And remember, neutral nucleophiles will lose a hydrogen when they form their new bond. So again, my nucleophile is going to react with one of these carbons in the triangle. Okay. It's going to attack. This is going to open. But when I attach this, I'm not going to attach it as H2O. I'm just going to attach it as OH, one hydrogen. It's got to lose a hydrogen when we add it to our epoxide. So again, start with my 2 carbons. Each of them now have 2 methyl groups sticking off of there. Okay. My nucleophile has attacked that green carbon, but again, when I add it, it's just going to be an OH. I'm going to lose a hydrogen for a neutral nucleophile. And my other carbon now has that, actually also an OH group, but specifically this oxygen is the one that used to be in my epoxide 3-membered ring. Okay, so this is what we saw before in chapter 6, when we first talked about nucleophiles. We can have negatively charged nucleophiles. That negative charge will become our new bond. We can have neutral nucleophiles, and if we have a neutral nucleophile, it's going to lose a hydrogen. And these are all going to be involved in these epoxide ring opening reactions. All right, and so all these examples were with symmetric epoxides. So let's say, what if I had something like this? This is now an asymmetric epoxide. So if I react this with a nucleophile, I would get a different product depending on which carbon in my ring that nucleophile attacks. Right? It can hit this blue carbon over here, or it can hit the green carbon, and I would get a different product depending on which carbon it attacks. Okay? So, let's see who remembers. Let's take a poll. Who thinks it's going to be the blue carbon? And who thinks it's going to be the green carbon? Awesome. Why are we going to do the green carbon? Less crowded, right? A fancy word for it would be sterically hindered. It's less sterically hindered, but absolutely, it's just less crowded. It's more accessible, and so the green carbon is what gets attacked. Oops. And my ring opens. Okay, so for these asymmetric epoxides, we can just make a note. Asymmetric epoxides, nucleophile attacks the less substituted carbon. Okay, so everybody take a second and draw the product. Make sure that we can do these ring opening reactions, getting the products of them. I gotta be good. There's gotta be some source of proton here, some solvent. All right, so most basic thing is we better have the same number of carbons on both sides. Right, so 1, 2, 3, 4, 5 carbons in my epoxide. So I need to have 5 carbons in my product. I can kind of keep track by coloring those blue and green carbons again. My green carbon has that new nucleophile carbon bond. All right, and it's a negative nucleophile, so I just replace that negative charge with a bond. All right, and then the blue carbon then still has that epoxide oxygen attached to it, so that's where my OH group forms. All right, so this was our last section of this discussion of ethers. An epoxide is this very specific type of ether that's this three-membered ring, and three-membered rings aren't really stable, so epoxides undergo these ring-opening reactions with nucleophiles. All right, so now let's rewind in our minds back to the beginning, when actually the first thing we talked about with ethers were ethers as a solvent in two of these what are called organometallic reactions. They're named after people. Grignard reactions and Gilman reactions. Okay. So let's do an example of each here. Let's see if we can't remember what's going on. Whoops. This has to have a... Okay, so both of these reagents have these metals attached to them. So for the Grignard, you got a magnesium. For the Gilman, it's a copper. In both of these reactions, you're forming new carbon-carbon bonds. All right, and the carbon that you're going to be forming a new bond with is going to be at the base of that metal for both of these reagents here. All right. Question being, which one in my other reactant do I form my bond with? In the case of the Grignard, it's going to be a carbonyl carbon. And in the case of the Gilman, it's going to, you're using an alkyl halide, so it's going to be the carbon that's at the base of that halogen. Okay, so this is my new bond that I'm forming here, is between these two carbons. So I'm going to start by drawing my one reactant. We'll do these 1, 2, 3 carbons. Okay, this was my carbonyl carbon, so I'm going to draw this new bond. All right, that makes this that orange carbon from over here. So now I got to just attach everything else. 1, 2, 3, 4. So 1, 2, 3, 4. Okay. The only thing that I'm missing is this oxygen from my, what used to be a carbonyl group. It doesn't go anywhere. I don't lose that oxygen, but I do break that double bond and it becomes just a single bond. All right, so the product of our Grignard reactions are always alcohols. Okay, with a Gilman reaction, we do actually kick off that bromine, so I'm not going to have that bromine in my product. I'm just going to replace it. Okay. All right, but the special thing that with a Gilman that we had to remember is if we have a double bond when we create our new bond, it has to be in the same direction as our old bond here. We have to preserve our stereochemistry. So the bromine's sticking up on my reactant. That means my new bond has to be sticking up in my product. Right? So here's my carbon at the base of the halogen. When I draw my new bond sticking up, that means that this has to be the orange carbon from my Gilman. All right, and with Gilman's, it's like it's got this set of carbons and then a 2 here. We don't want to get bogged down on the 2. It's really only one of those R groups that are going to be added. So in this case here, I'm just going to finish this off by drawing my other carbons. Whoops, let's use the correct color. All right, and again, we preserved our stereochemistry, so we started out with this cis alkene over here, and it remained a cis alkene over here, right? That's what we have to remember about our Gilman, is that they will preserve the stereochemistry of an alkene. Okay, and then one more thing that we can do with our Grignard, and these were like the trickiest of your homework problems here, was turning a small alcohol like this into a much larger alcohol like this. All right, how can we use a Grignard reaction to do this here? So let me swap these. Okay. All right, so step 1, I want everybody to look at our product here and see if you can't find where the new carbon-carbon bond is. Right, Grignard reactions create carbon-carbon bonds, so I gotta have a new carbon-carbon bond going from reactants to products. Where in this product here is my new carbon-carbon bond? So let's go 1, 2, 3, 4, 5. Which one do we think? Between which 2 carbons? 2 and 3. Okay. So we have this 2-carbon alcohol here. The important thing is that this carbon with my oxygen on my reactant side is going to stay or keep that oxygen on my product side. Right? So these 2 carbons must be my original alcohol. So this thing here is my new bond. Great, so we can use a Grignard reaction to create that bond. The problem is, do Grignards react with alcohols? No, they react with carbonyl carbons. Okay, so what made this assignment tricky is now we got to pull from our knowledge of the previous chapter. All right, so I'm going to put down a list of reagents here and see if you can't remember which one would do this for us. All right, I need to convert this into a carbonyl group.
That's an oxidation.
That is an oxidation, exactly.
DMP.
Yeah, so we have two oxidizing agents here, okay? DMP and this one, but remember this one, this sodium dichromate is a strong oxidizer. That would actually give us a carboxylic acid. We want to use the DMP, our weak oxidizer, so that we get a carbonyl group. All right, so then what would be my Grignard reagent that I would react in order to get to our product here? So everybody take a second and see if you can't fill in what should go here. What other reagent would we use? Oh, and yes, sorry, this was what we concluded was that we would use our DMP here, our weak oxidizer. All right, how many carbons should we have in that Grignard? What are we missing? Not 2. 3, right? We got 1, 2, 3 carbons we need to attach. So I'm going to have a 3 carbons here, and then I'll put my MgBr because we need to attach this carbon, whoops, to my carbonyl carbon. Right, so again, actually both of these reactions create new carbon-carbon bonds, right? So we can take a smaller alcohol and convert it into a larger alcohol using these Grignard reactions. All right, so I'm going to take this list of reagents here, put it up so we can have something to look at, and now y'all are going to do one on your own for me. Okay, tell me how we would go about turning acetone, this thing here, let's do into this thing here. Again, using a Grignard reaction in the process. Oh, crap. I'm going to get rid of this. Sorry. I made it too easy. 2 propanol into this alcohol here. All right, so again, I got to figure out where my new bond is here. And the one thing that I know for absolute certain looking at this is that this carbon here attached to the oxygen has to be this carbon here attached to the oxygen. All right, that's what I know for sure. So then if I have these 1, 2, 3 carbons in my alcohol, they're going to have to be these 1, 2, 3 carbons in my product alcohol. All right, so that means my new bond has to be this thing here. All right, so now I can go about setting up my Grignard reaction, but again, alcohol groups will not react with Grignard reagents, so I have to perform an oxidation reaction. Which one of my reagents am I going to use? Well, so first of all, this one, not an oxidizing agent, right? That would turn that alcohol into a chlorine. That's not going to help me. This one, not an oxidizing agent. That would turn my alcohol into a bromine. Not going to help me, right? So these are my 2 oxidizing agents. And in the case of this secondary alcohol, it actually doesn't matter which one I use, right? Previously, we had to use the weak oxidizer, so we didn't get a carboxylic acid. In this case, either one of these would give us the same ketone. Because remember, if it's on a secondary carbon, it can't be turned into a carboxylic acid. So I could use DMP or that sodium dichromate in sulfuric acid in the presence of water. Either one of those would work to create my carbonyl group here. Okay, so now I can turn around and react this with my Grignard. The key thing that we got to pay attention to is the size of our Grignard here. We need to have these 1, 2, 3, 4, 5 carbons on there. I'm just going to kind of draw it as it is in my product so we can see a little bit easier. Okay, and the new bond forms between my carbonyl carbon and the carbon that's at the base of that MgBr. All right, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Boom. Okay, so these were these organometallic reactions. They kind of are a little bit out of place in terms of this chapter because this chapter is about ethers, but remember, ethers are the solvent in which these reactions carry out. And these reactions are really important in organic chemistry. They work very well. They're one of the first types of reactions that you would do in the lab. So that's why they put it in here. Okay, when we're talking about reactions of ethers, we said ethers are actually pretty boring functional groups, all things considered. Really, we learned about 2 types of reactions: how to synthesize ethers and how to break them apart. Okay. All right, and what we want to be able to do is, given an ether structure, we want to be able to figure out the alcohol and the alkyl halide that we would use to synthesize that ether. Okay, as well as the product if we had that ether in the presence of a strong acid, which will decompose it into an alcohol and alkyl halide. All right, so for both of these types of problems, we're sort of going to start in a very similar way, where we're going to identify the degree of substitution of the carbon on either side of our oxygen. On the left-hand side, we have two neighbors, so carbon neighbors, so this is a secondary, versus on the right-hand side, we have a primary. Okay, so same thing down here, we just have the same ether. All right, but what we do with that information is a little bit different depending on the reaction. So when we're doing the synthesis of ethers, okay, the key here is that the less substituted carbon is our alkyl halide fragment. So if I look here, I'm going to split this ether into two halves. One half will be my alcohol, the other one will be my alkyl halide. My alkyl halide will be on the less substituted carbon. So that means I have this 2-carbon alkyl halide here, and the other chunk is my alcohol. One other thing that that I could ask you and your homework's going to ask you is, instead of the alcohol, remember the first step is to do this acid-base reaction with sodium hydride. So it could instead ask you for what's called an alk oxide ion. All right, and that's just where you take your alcohol and erase that oxygen or that hydrogen and replace it with a negative charge, right? So the deprotonated alcohol is what's called an alkoxide ion. Boom. Okay. When we're talking about our decomposition of ethers, we're going to do the same thing. We're going to determine the degree of substitution of the carbons on either side. But then we had to remember that we created this like reactivity series here, okay, where we ranked each type of carbon, methyl, primary, secondary, and tertiary or benzylic, based on how reactive it is. Okay, so tertiaries are actually the most reactive carbons, tertiary or benzylic, and then it just goes in order of size. So in this particular example, we're comparing a primary and a secondary. We can see that the primary is the more reactive carbon. All right, and the more reactive carbon becomes our alkyl halide. So in this particular example, I get basically the same two products. My alkyl halide fragment is that 2-carbon fragment, my primary alcohol, or my primary carbon, the more reactive carbon. And my alcohol is the other chunk. All right, so that is a quick summary of all of these reactions that we learned from this particular chapter. Last week's homework was those organometallic reactions. This week's homework will focus on our reactions of ethers, as well as what we discussed at the very beginning with the epoxides.